Okay, now we'll go to the last section, remote sensing applications. And first we're going to look at space probes that have SAR systems on them. And what I want this to be is, not a remote sensing lecture, but give you an idea of the history of how SARs have evolved as remote sensing sensors, and the different missions and platforms that exist out there, and what's happened to them, and where we are, where we're going. And the first SAR was the Venera 1516 from Russia, and that was in the early 80s at an 8-centimeter wavelength. That's a little lower than S-band. And then Magellan went up to Venus. We've taken a look at that. We're going to look at Cassini going to Titan, the biggest moon of Saturn, and Chandrayaan-1 from India. They lofted a mini RF SAR with 12-centimeter wavelength. And then there's a Lunar Reconnaissance orbiter that was sent up in 2008. Now, here are Earth viewing satellites. And wow, do we see a lot of action going on internationally. The first was CSAT. I noticed that when I pointed that out to you when we were looking at the history. But then the SIR ABCs were satellites with SARs. These first two missions, this one was just L-band and then LC and X. And then there was another mission with vertical antenna so that height could be measured, the so-called SIR-Cs. Then European radar SAR #1 from ESA, the European Space Agency. Japan, Canada has launched a radar sat that have these resolutions. There's Terrasat from Germany, Cosmo from Italy, TechSat from Israel, Lupe from Germany, and India and China. And different polarizations and different resolutions up to the present is what I could find when I looked around for things. Now let's look and see what we see. Here's a nice close-up. I showed you just a very small, but at least on my nice wideband screen it's easy to see, of the first U.S. satellite with SAR capability, and it was the first one put up. Well, Venera, was up ahead of it. It's the first satellite with SAR capability, and it went up to 78 L-band. And here's its antenna, and I bet it's an altimeter, and the solar arrays, and the guts of the system were in here. And that used analog processing, remember. And the waves off, this is for wave motion, you can see off Alaska's southern coast. I pointed that out earlier. And note the glaciers on the land. That's just amazing. And then, so this is how the arrays were positioned. Here's the C-band array, and here going down is the X-band array. And they were NASA's mission to planet Earth, they called it. And it's the SIR-CX SAR. And these SARs illuminated the Earth and got really fantastic data, regardless of weather or the conditions. And it also, the CX SAR, there's also an L-band radar, and C and X, and the multi-frequency data was used by the whole community around the world. And this SIR-C, which is the SAR, was developed by JPL, and the X-band radar was developed by Alenia and Dornier for the German Space Agency, and the Germans, DARA, and the Italians. So this is an international effort that went on the shuttle. And here is the shuttle radar topography mission, and they put out a boom, and 60 feet out from the main antennas, and the radars operate at C and at X-band. And on this particular mission, the L-band radar wasn't used, and a 60-foot boom was sent out there so that you could get two different reflections at C and an S-band, so we'd be able to get height on a single pass. Remember I talked about that with the interferometric SAR, and that's what we go talk about here in the phase difference between the two measurements that you transmit and receive here and here. That'll give you the height at a point. If you want to know the algebra, go to Roger Sullivan's book. Here is some really neat images. When you have one set of data from one sensor and one set of data from another, and you combine it, boy, can you get some beautiful images. And this is courtesy of NASA and JPL. And what they did is they took Landsat visual imagery, and it was draped over the elevation data from the SRTM mission. And coral reef fringes of the islands, many locations appear as light shades of blue, and the tropical vegetation is green. And you know, they played the game because Landsat will tell you the type of vegetation so that you could see this beautiful 3D map. I'll tell you, one of the best vacations I ever had was in 1980, the winter in February. And this is Sir Francis Drake Channel. And my wife and I bareboat chartered. We were dating at the time, and we and another couple bareboat chartered up and down Sir Francis Drake Channel for a week. It is gorgeous, just gorgeous. And this is only 25 miles, and there are about 25 beautiful harbors. And this is St. John's in the U.S. Virgin Islands and St. Thomas. We came out of St. Thomas and then went over into Tortola and then back and forth and back and forth and up the Virgin Gorda. And actually, we stayed. You have to stay within the channel, and you just go out to Joost Van Dyke and back. It's one of the rules. But anyway, the reason I remember it so fondly is after we came back from the cruise, my wife and I got engaged. And the SRT Interferometric SAR here we have draped some digital elevation data on optical imagery is draped over the IF-SAR imagery. It's from the SRTM. And this is the Kamchatka Peninsula. Notice the beautiful image you can get from, you know, a perspective that you wouldn't get from if you were looking straight down. And you get that altitude by looking at the two different ranges that are offset. Get the altitude. Now you can also make some fantastic imagery. This is in Death Valley, and you can show the smoothness and roughness of the area. And so down here, the different colors represent the reflections, the different polarizations transmitted and received. And you just can imagine what this is just, it's not a food, it's a banquet for scientists and geologists who study the Earth to understand the nature of the geology of the land masses and the planets. And if you just go and, as a matter of fact, today I received in the mail a special issue of the IEEE Proceedings, and it's about that thick, and it's on high-resolution remote sensing. And all of that data is using SAR techniques for the most part. There'll be, I'm sure, some articles using infrared sensors that will get angle data, but I'll bet you dollars to donuts I haven't cracked the issue yet. An awful lot of the very fantastic articles in that will be with satellite-borne and airborne synthetic aperture radar systems. And here's an active volcano over in Japan. I'll just leave these up in color so you can see them. And the volcano occupies a peninsula in the center of this bay, which was formed by the explosion and collapse of an ancient predecessor of that volcano. So you had a volcano here, it collapsed in, and out comes this other volcano. Just beautiful to see. And lastly, here's some more Sura images where we take, here's a volcano on one of the Canary Islands, and it shows all the different features of that. And this was on the Space Shuttle Endeavour. And this is courtesy of NASA. And here's an image. This is the European Space Agency's Ursa 1. And here we can see an oil spill off the coast of Portugal. Very nicely mapped. That's from 1994. And here's their solar arrays and their panels. And I'm sure that's probably a telemetry or the altimeter for the system. Now here are some Ursa 1 images in black and white of glaciers in Alaska. Here are some images of Canada and Alaska. Here we have an ice shelf on Ellesmere Island. This data was taken with ERS-1 in 1992. And the ice shelf out here is the dark gray between these mountains. And then you can see ice beyond, sea ice beyond this ice shelf. Here we see a glacier in Alaska. And it's got a dark core surrounded by bright radiating lines, and the open ocean at the top is at the top of the picture. And there actually is, it didn't come out in my JPEG, but there is a dot. If I look very, very, very finely, you won't see it. There's a ship that can be seen. The wake of the ship that's dark can barely be seen. To see that. Now we go on to Canada's radar sat. And I like this because this is an image of Lake Vostok in Antarctica. But it shows, first of all, the international nature. But this particular radar had all these missions, all these remote sensing missions. And I'll just say them to show you the diversity of what you can do in remote sensing with these. Ice sea monitoring, cartography, glacier monitoring, forest cover mapping, oil spill detection, assessment of the likelihood of mineral, oil, and gas deposits, urban planning, crop production forecasts, coastal surveillance, erosion of the Arctic shelf and Antarctica, and up in the Arctic, and surface deformations detection. An amazing amount of knowledge has been developed. And if you Google Scholar remote sensing, you will get incredible numbers. Too much for you to see. You'll have to pick forest cover mapping to get down to hundreds upon hundreds upon hundreds of technical papers, journals, really first-rate stuff that's been published with these Earth observing remote sensing satellite systems. And here's another one of Antarctica. And the shaded relief area, it was developed by, it's Canada, you can see that. And there's a little, here's 1,000 kilometers. This is courtesy of NOAA. Now we go to space probes. We've got Venera, Magellan, Cassini, Chandrayaan, and Lunar. And here we see Venera. It was launched, 15 and 16 were launched in 83, and both contained SAR systems, and they just imaged the northern hemisphere down to 30 degrees. They had just 1 to 2 kilometers, not the 150-meter resolution. Magellan, both missions were successful. I couldn't find any images to be able to present, and they may be seen at this website below, but there's a whole issue of copyrights, and that I can't put something up. That image here is courtesy of NASA, but this image is not for public dissemination. But if you just put in that URL, you'll be able to see images that Venera took back in '83. Now here we go looking at Magellan again, and here's the big picture of Magellan. And when we look close up, with the 150 meter by 150 meter resolution, we see the Alcott crater. When you when you discover these, you get to name them, you know. And in Venus, so that shows you, you know, the kind of resolution you can see. And here's a crater in the Navka region of Venus, and it was mapped by Magellan, so it was named by Venera, I'm sure. And the crater has a diameter of 22 kilometers, terraced walls, and there are all classifications of these craters. And the central peak is on its floor, and that's unusually large. And you can see the flow deposits going out. And Buck, the proposed name for this crater, honors Pearl Buck, the American author. And now we see Magellan images from the left and from the right, and this allows you to get a perspective when the sun is looking one way and is looking the other, so that you can get some stereo aspect. In this case, we're looking at troughs in the Lavina region of Venus. And these troughs are 100 kilometers in length and in width, and the full resolution mosaics 14 orbits of the Magellan sensor. So we've got 120 meter resolution with this data. It's very useful to having right and left, because features that are not visible when you're looking from one side, you can see with the other. And this is an image of the longest channel on Venus with the 120 meter resolution. This is a compressed resolution mosaic. It's a 600 kilometer long channel that's this is a 360 mile segment of the channel, and it's the longest channel discovered on Venus, and it's about a kilometer, 1.8 kilometers wide, and the ridges are 7,000 kilometers long, and it's longer than the Nile River, and so it's the longest known channel in the whole solar system. It was originally discovered by the Soviets, and in most places it's 1 to 3 kilometers wide, and it may have been formed by lava, which may have melted or thermally eroded over the plains. Now we have get one of my animated images here of Cassini, and this is the Cassini-Huygens space probe, and this is the flagship. Is a flagship class NASA ESA ASI spacecraft that was sent to the Saturn system. It's launched in '97, and a probe landed on the moon of Titan. It was called Huygens, and it surveyed and then landed on Titan. And we're going to see in a minute some of the survey. And Cassini's instrumentation consisted of a large suite of sensors, and just one of them was the synthetic aperture radar, which was used for mapping the surface of Titan. And here we see those images. This is 90 kilometers in size. This is a large lake in Titan. It's the size of Ontario, and it's called Lacus. And it's in the southern hemisphere of Saturn's moon Titan, and it was obtained by the Cassini probe. And here are the attributes of it. And there's a rare impact crater on the moon, 25 miles in diameter, and in the new volcano here, surrounded by ejecta material. There's a new, and that's all the ejecta material. So, and there are 350 meters per pixel on these images. Okay. And Chandrayaan-1 was an unmanned lunar probe. It was launched in 2008, had a mini-SAR on it, and with these characteristics. And it had some things that work, and it had problems with some of the experiments. And it would hope to find to find polar ice with it, but it wasn't able to. And that was a synthetic aperture radar. But it had problems. And lastly, the Lunar Reconnaissance Orbiter, which operates at these frequencies. And they attempted with Chandrayaan to do a bistatic radar experiment, but that didn't work. And in 2011, after it completed all its missions of Lunar Reconnaissance, it suffered a critical failure, and it no longer produces useful data. Now, and that's really what's been going on in space and with these remote sensing systems. One can imagine just the huge amount of stuff, of data that's been collected with airborne systems, which I haven't shown you. Well, let's summarize now. It's synthetic aperture radar. You can see it's just been incredibly useful technology, both military and in the remote sensing field. You can get fantastic range, cross-range resolution, that big. And the focus resolution is not a function of range. You got to remember that. And the resolution improves with collection time. You want long synthetic apertures, but you're limited by that d/2, the size of the antenna, and the long track dimension, and intensive coherent processing you need to do to really exploit image formation and very, very precise motion measurement to compensate for the motion of an aircraft in the air, the phase if you're moving in a straight line, the buffeting of a plane, and you need very, very precise GPS measurements over and above what GPS gives you. You need to, if you put satellites up, you have to put TOPEX satellite, which is an altimeter satellite, a few years back that I didn't talk about. It has a couple of centimeters. Its object was to survey the ocean and measure currents. Just on the data, that TOPEX satellite, which I didn't mention, did 86,000 revolutions around the Earth, collecting altitude data. And in 2012, they had a 3-day symposium in Venice, huge conference proceedings of all of the stuff that had been done by that excellent altimeter measuring satellite. And after that was put up, and the TOPEX was put up by the U.S., another one was put up, Jason 1 and 2. It would go around and measure the altitude every 114 minutes. And the data from it, 2 centimeters ocean height, was so good that they sent up, nearing the end of the expected life of 4 years of TOPEX, they sent up Jason 1, and they put it in the exact opposite place in the Earth. So rather than collecting in the exact same orbit, except it was, at the antipode, so it collected data not every 114 minutes, but 57 minutes. And so for years and years, they've worked very well. And it turns out these have to be oriented very, very well, like 1/10 of a degree pointing accuracy in order to measure the wave height, you know what I mean? And so what you have is another piece of the satellite. The whole satellite weighs, I think, it's like 1/2 ton, something, the order of that, and only 1/5 of it is the radar altimeter. But you have a lot of other instruments to perfectly align the radar antenna, the satellite, so that it's pointing exactly to 1/10 of a degree towards this one point on the Earth, while it's collecting data and blasting away and receiving pulses. And what it has is a set of sensors that measure 327 stars, and that they know the locations of in space. And it goes and it takes an image of space and says, "Oh yeah," and then it goes with a set of wheels and stuff, and just servos, keeps the TOPEX satellites and the Jasons just on orbit. And that's why I say that, because to emphasize the precise motion measurement and compensation needed for these are huge technologies, and automation and more analysts. It's just huge volumes of data exceed the capacity of the analysts to measure, typically with these sensors. Okay, now on to homework. The good news about this is that these are similar to the example problem that I went over in the lecture in the first, I believe it's the first section, swath widths, footprints, cross range and full range resolution on the ground. This is really the same setup of the problem, but some more questions. And then derive the equation for the height of a SAR shadow for a round Earth. And here are the references. And you can see 2 pages of references. I'm going to dwell on these. Merrill Skolnick has come out with 3 editions. And his 3rd edition of his Introduction to Radar, he has about nothing on SAR. But in his 2nd edition, if you just want to read 11 pages on SAR, it's a nice 11 pages to read. And it's pretty simple and pretty easy. Jerry Bennett's taught at Lincoln Laboratory a great lecture on synthetic aperture radar internally, and I used a lot of Jerry's view graphs, and I thank again the laboratory for being so kind to let me use them, and Jerry for doing such excellent work. I feel that when I sent Jerry to proofread, oh yeah, any errors in these last 2 lectures, send me them, and if they're gross, I'll fix them. But I wanted to bounce by, to an expert. I sent a PDF of the view graphs to Jerry, and I feel that I received the consummate award because he said, can I use some of your view graphs that you developed? So when Jerry Bennett's asked me for view graphs, I guess it didn't do too badly in the development of the work of the view graphs. Anyway, there's Roger Sullivan, who, by the way, I've known for 50 years. This is my 50th year reunion for MIT. And when I first year I was a freshman, I met Roger. He was a year or 2 ahead of me. And Roger was also a physics major, and Roger got his PhD in physics at MIT, along with his undergraduate degrees. And Roger, first, he's done a splendid work at first at IRM, and then at IDA in synthetic aperture radar work. And then he's worked at the Pentagon, and then back at IDA he's working, and he's retired. He must be 73, I guess, but he does part-time work. Anyway, Roger wrote a great book published by SciTech called The Foundations of Imaging and Advanced Concepts. But then when Merrill Skolnick put together his 3rd edition in 2000, what he did was he asked Roger to write the chapter on synthetic aperture radar, and that chapter is 45 pages long, approximately, as I remember. So if you don't want to read the whole book, you go here. If you want it in more detail, you go here. And to find out the details of some aspects of the spotlight synthetic aperture signal processing algorithms, this particular book is a great one. It's I bought one used from Artec to put together to teach myself to use the book. And here are 2 other synthetic aperture radar books, which are more in detail. And then we get on to Jerry Bennett's fantastic high-definition vector imaging. Oops, that error I won't change, should be a capital I. And the Lincoln Lab Journal, which if you're at a U.S. university, it's probably on the shelf. If you have a decent engineering department, one goes to most of the major science and engineering laboratories, or you can get it right from the web. Just say hi, definition, vector, Bennett's on Google Scholar. Bing! This will come up and you can download the PDF. And there's a lot of great images on this NASA website of the SRTM data. And I wanted to point out the Baum article on, it's in the Transactions that was in '92 on remote sensing. This points out a very, very specific, neat stuff that Balmer did. which I talk about and I reference that are on page 706 of the transactions of the IEEE and remote sensing and geophysics. But also I want to add, if you really want to see some up-to-date stuff, the proceedings of the IEEE, the latest issue, which arrived in the mail for me today, is here. And here is, it's back a ways, but 3 by Ullaby, who has written the classic undergraduate electrical engineering, electromagnetism book. He's got these 3 volumes out with other authors on microwave remote sensing. They're somewhat dated in that they're in the 80s, but they contain a lot of useful information to look at. And you know, you can go on and on. But anyway, those are the references. And lastly, incredibly, I'd like to thank Jerry Bennett for all his help. And also I'd like to thank Eli Bruckner. Every now and then in the course I'll have a question about something and give Eli a call. He's just a hop, skip, and a jumping away. And I'd like to very much acknowledge his help.